So, let's start off with an equilibrium reaction. Notice the double arrow in the middle of that equation. That's your representation that it's an equilibrium reaction. That means reactants form products, but then those products can bump into each other and reform reactants. So there's a forward reaction, there's a reverse reaction. This is constantly happening. At some point, equilibrium is reached. So at some point, there's a balance between the amount of reactant and products, or the concentration of each is what I say for that third bullet point. That is not necessarily a 50-50 balance, as you will see today. Again, we tried to bring that up a little bit in Chem 1 without talking math. Quite frankly, it might make it a little bit easier with you guys that we can start to talk about mathematics behind it. Doesn't matter how much you start with. You could only start with reactants. Well, then the reactants start to form products. But now I have products that start to form reactants. And I get that balance. You could start with only products. Well, now they form reactants. And now I get that back and forth again. You can start a little with both. In an equilibrium reaction, each particular reaction at a given temperature will establish equilibrium. Will establish a certain balance that is met between the reactants and the products. Does that ring a bell? You know, the analogy as you're kind of finishing up writing down for this first slide, because I'm going to click the link to show a little animation about this as well. The analogy I like to use is, this was almost 20 years ago. I went to Hawaii, and there's a beach in Kauai where there's lava rock in the ocean surrounding it. So there's kind of a penned-in area for the water, which is kind of nice because then you don't get pulled out because the rock breaks the waves. At any given moment, there's people in the water, there's people on the sand. But some can also go into the water. Now, if the water gets too full, now people are going to go from the water back into the sand, and there's this flow that's constantly happening. So even when equilibrium's reached, that doesn't mean things have stopped. That doesn't mean once you're in the water, you have to stay in the water. People that are in the water can go up back onto the beach, but now if the beach gets a little too full and people are bumping into each other too much, some might go in the water instead. So again, I'll show you the little animation here to go over this. Sure. As a reminder for you. In Chem 1, after we talked about equilibrium reactions, we talked about what happens if it now is disturbed. What happens if you disturb equilibrium in a way? For example, in my beach analogy, what if someone spots a shark? We're not going to have the same amount of people in the water as on the sand. There's going to be a huge shift towards the beach. I don't know, maybe there'll be a few people that then want to go from the beach onto the water with their phones to take a picture of it, or they're thrill seekers, who knows? The Logan Drizens of the world. Yeah. Le Chatelier's principle is referring to when you have a system that has a stress applied, or again, you've made it no longer balanced, the reaction will re-establish that balance. So the example I'm going to show you is the reaction I have up on the smartboard. Again, this is kind of fictional reaction, but again, the online textbook, the old online textbook, has a video that will go over this as well. Now notice I have a delta H on the far right-hand side. Notice that's a positive value. That must be an endothermic reaction. That's kind of an important thing to recognize as we're doing this. The three stresses I have below the reaction, if you change the concentration of a reactant or a product, that no longer makes it balanced. It has to reestablish balance. If you increase or decrease the temperature, it will change the balance. And lastly, with gases, if you change the size of the container or the pressure at which is being applied, that will disturb the balance as well. So I'll kind of talk you through these three a little bit, but then I think the animation does a good job of showing it because, again, just like the example that you saw a minute ago, some equilibrium reactions, especially when they deal with colored species, are really good to observe this change with, because then the shade of the color tells you the balance between the reactants and the products. Like we have a piece of equipment that we use to tell the color of things and the concentration then. That's where they get some of this data from. Okay, change in concentration. If this reaction I have written up on the board is at equilibrium and there's a certain balance between reactants and products, and then I all of a sudden add more of either A or B, that increases the odds that these reactants can bump into each other, which means they will, which means they're going to create more product. So if you add more reactant, it's going to shift towards the product side to reestablish that balance. Similar thing could be said as if you add more product. I know what feels weird about this is saying product and you add more of it. You want to think they can only add reactants, but that's not the case. In equilibrium reactions, even though it's reversible, anything on the left side of the arrow is considered a reactant. Anything on the right side of the arrow is considered a product. So if you add more D, the reaction would shift back towards the reactant side until balance is reached. You could take something away. Now, it's not like we have little tweezers that can grab the letter D or the whatever D and take it out. More likely what would happen is if you added something that would react with D. And we'll kind of go over that a little bit more with like acid-base chemistry. If you had an acid on one side of these, and then you also added sodium hydroxide, a base, it would react with it, it would use it up. You're taking it away. Well, if you took away letter D, for example, C has nothing to collide with anymore. So the reverse reaction slows down, but the forward reaction just keeps on going. So it shifts to create more of that to get back to that balance. As for temperature, in Chem 1, what I told my students is if you recognize, based upon the sign of your delta H, positive or negative, this is endothermic. I would almost rank heat as a reactant then, because in an endothermic reaction, you have to put in more heat to make it occur. So now, if I say heat is added to this reaction, it's just like adding a reactant. And if you add a reactant, it shifts towards the products. If you take away heat because you cool it down, put it on ice, well, now it would shift in the other direction. Temperature, by the way, is tricky because temperature is the one variable of these three that can actually change that equilibrium constant value, K. Again, I'll talk a little bit more about the K value after we finish up review of Le Chatelier's, because that's more in the math than new stuff. Finally, temperature and pressure. If I look at the left-hand side of this equation, I see 3 gas particles total, 2 A's and 1 B. If I look at the product side, I see 5 gas particles total. The easiest way to think about the temperature-pressure relationship is smaller volumes favor fewer things. So in this particular reaction, if I were to decrease the volume, it would shift towards the reactants. Now, the best way to think about it is if you decrease the volume, you're increasing the odds that these things will collide with each other to make that. In order to relate that to pressure, you have to remember Boyle's law is the inverse relationship between pressure and volume. Therefore, if I'm saying that I'm decreasing the volume, it's the same as increasing the pressure. Again, I'm going to click on the animation to show you that video as well. Hopefully, that has provided a little bit of a reminder of what we did in Chem 1. We talked about what is an equilibrium reaction and how to reestablish equilibrium. What I have to go over now is the math that we have to be aware of to start. Similar to thermodynamics, where each class period I kind of introduced to you a new way to do enthalpy, I'm going to do a similar thing here for the next few days as well. I'm going to introduce to you a new way each time to go over how to do equilibrium math. The generic equilibrium reaction I've written up on the smartboard in the middle there. Uppercase K, not to be confused with lowercase k, which is the rate law constant. Uppercase K is the equilibrium constant. And as the first animation showed you, to solve for the equilibrium constant K, you take the concentration of the products divided by the concentration of the reactants at equilibrium. And that is raised to their stoichiometric coefficient. Now, underneath that main equation, which I believe this first equation is given to you on your equation sheet. Yep, it is. Underneath that, I referenced the fact that equilibrium could be expressed based upon molarity, Kc for concentration, or based upon pressures in atmospheres, Kp. Some of the videos I showed you, and some of the main equilibrium reactions that are out there, are gaseous ones. My third bullet point after the equation states if you know the concentration or the pressure of everything at equilibrium, you can solve for that K value. Now, to be honest with you, a lot of K values are already known. However, you might have to actually do the practice of solving for K. The very last thing I have noted in italics. The numerical value of K helps to show you what is the balance between reactants and products. Because typically it is not a 50-50 balance. If the K value is a lot greater than 1, like 5,000, 5 million, 82, I don't know, whatever. If it's a lot greater than 1, hopefully mathematically you can realize that means you have more products than reactants at equilibrium. It's kind of product favored, if you will. So you look at that K value. If it's bigger than 1, there's more products than reactants at equilibrium. However, if it's smaller than 1, and this will in particular come into play when we do acids and bases, 1.8 times 10 to the negative fifth. Again, that's the same as 0.000018. That's a number a lot smaller than 1. If the number's a lot smaller than 1, there's more reactants present at equilibrium than products. Again, think about it mathematically. Products over reactants. If there's more on the numerator, it's a big number. If there's more in the denominator, it's a small number. So one of our goals today is to be able to look at that K value and just flat out be able to state, hey, there's more products at equilibrium, or there's more reactants. Then, what happens if we add something or take something away? How does that shift our balance to get back to equilibrium? Because if you took away a whole bunch of A, that would also change this. It would change your denominator a little bit. So it's got to work backwards to get to that K value. So this slide is talking about what is the K value, and if I gave you the concentration of everything at equilibrium, I gave you a balanced equation so you could use the coefficients, square it, take it to the third power, you could solve for the K value. My last slide is going to refer to more of, if you are given a K value, what can you do with that? Because just like Appendix 2 in your textbook gives a whole bunch of delta H's and other things, there's K values for a lot of these things as well. So, here's the equation I'm giving you. And I'm telling you that the K value is 100. 2A plus B yields 3C plus 2D. If instead this was the reverse reaction, as I've shown on this next main bullet point, the K value would have to be products over reactants kind of flipped. So it'd be 0.01 instead. If we calculate K by saying products over reactants, we have to look left side of the arrow and right side of the arrow. Because that's what determines what the products and the reactants are. So when I show you this second equation here, if you recall enthalpy, we would just flip the sign for a reverse reaction. We'd multiply by -1. Remember Hess's law just a little while ago? But for equilibrium, this is more of a multiplication type calculation rather than addition subtraction. So the way that some people might express this is that if you know the K value and you want to solve for K1, it'd have to be 1 over K. Because you're doing the flip of products over reactants and you're now switching them around. Does that make sense? If I go from this to this, all I'm doing is flipping the equation around, which means if in this top equation there's more products than reactants, the bottom equation there must be more reactants than products. It's the same thing, just in a reverse order. The last thing I have is notice the difference in this last equation versus the first is I just doubled all of the coefficients. Now, if we think back to Hess's law again, if I doubled it, then you would have multiplied by 2. However, to solve for K, you have to take things to the power of their exponent, not multiply them. So when you have a 2 in front of this A in the top equation, it's the concentration of A squared, not 2 times A. So if I were to double this entire reaction, what I do to solve for K2 is I have to square my original K value. 100 squared gives me the 10,000. So the beginning math that you're required to do is going to be a combination of, here's a K value from one reaction, now I give you a slight variation of it, solve for the K value. Or, here is the concentration of everything at equilibrium, solve for the K value. So you can expect to see a little bit of both when it comes time for WebAssign when it's dealing with that. You'll also see a little bit of Le Chatelier's principle, which is why I thought a good way to end class would to be giving you time to work on a few problems. I believe the first few are the K math variety. The last few are a little bit more Le Chatelier's. Now, the other things you picked up on the way in, quite frankly, this computer activity sheet, I just went over that with the video for you already.